A uniform bar of mass M and length L extends horizontally from a wall. A supporting wire connects the wall to the bar's midpoint, making an angle of 55 degrees with the bar. A sign of mass capital M hangs from the end of the bar. If the system is in static equilibrium, determine the tension in the wire and the strength of the force exerted on the bar by the wall. If M, the mass of the bar, is 8 kilograms and capital M, the mass of the sign, is 12 kilograms. So in a problem like this, anytime we're dealing with forces, the first thing we want to do is sketch out our free body diagram and fully identify what forces are actually happening in our situation. And so looking at our figure, first step, free body diagram. All right, we have the sign hanging at the end of the bar with weight capital M. And weight is always going to point in the direction of the gravitational field, so straight down. So we have the weight of the sign big M, so that's going to be equal to big mg. So that's our first force we can label. The next thing, it told us the bar itself has a mass, little m, and so we know the weight of the bar is going to act at the center of mass. And so it's a uniform bar, that means mass is evenly distributed. That means the center of mass is at that midpoint. So at the midpoint, we have the weight of the bar itself. Oh, it does not want to make a nice vertical line for me. That'll do. So weight of little m will be little mg. So that's the weight of the bar itself. So right now we have the weight of the sign and the weight of the bar. The next thing we can see from our diagram is we have this supporting wire. So there's going to be tension along that wire. And it's always kind of along that same direction of the wire. And it said that the wire also connected to the midpoint of the bar. So I'm going to label this T for the tension in the wire. Now it is at an angle, so we do want to consider the components. Now technically, if we're drawing a free body diagram for the AP Physics test, don't include the components on there, but if you're just drawing a sketch to help yourself figure out the situation, it's very helpful to fully label the components as well. So I am going to go ahead and include them. We have Ty, the vertical component, and Tx, which points to the left. And so that represents our tension. I guess I'll go ahead and just continue to look at the geometry here. They said they labeled the angle down below 55 degrees. Well, that means that this angle is also 55 degrees, or the angle in between T and Ty will be the complementary angle, or 90 minus 55, whichever way you want to consider that angle. The last thing, we know that over here, where the bar connects to the wall, there is some kind of interaction there as well. So there will be some kind of force. Just looking at our picture, we have a force to the left already, Tx. Well, if it's going to be in static equilibrium, that means we need a force to the right. So we can go ahead and imagine that some part of this has to point to the right. So we'll have Fx. Oh, it really does not want to draw a horizontal line. Okay, let's just go with that. Fx. And then again, just glancing at this, we have a couple of forces down, then we have the tension in the wire up. We could just imagine that Fy could also be upward. And so I'm gonna go ahead and draw it that way when we're actually working through the problem. Again, the direction will be determined by the sign of our answer, whether it's positive or negative. So it's okay to just make a prediction now, and then we'll be able to verify that when we actually get a numerical result. And so this represents, yeah, all the possible forces. We have the force on the bar from the wall, we have tension, and we have both of the weights.